Good morning, everyone. My name is Martin Buchacek. I came from the ETH, and first of all, it's an honor for me to be here and be able to present my results. And I really appreciate that the organizers gave me this opportunity. I will talk about a problem that was introduced in 1960s by Labouche. Then it didn't really attract attention for the next decades, and now it's enjoying a renaissance in the group of Johnny Blatter, with lots of work to be done. And in my project, I have extended the strong pinning theory to account for effects of finite temperature and creep. So first of all, a brief outline of my talk. I will remind some basic ideas of the strong pinning that were, some of them were already introduced in Johnny's talk. Then I will describe how we can treat creep in the strong pinning theory, in particular, how we formulate the problem in terms of the rate equation, and how we solve it. And finally, I will describe how we can use this to calculate the current velocity or current voltage characteristic. So before I do that, let me just flash this elementary slide. So we know that vortex motion in type 2 superconductors produces dissipation of energy, and in order to avoid this unwanted dissipation, we pin the vortices, and then the current velocity characteristic for a general pin system looks like that. It has a superconducting region for low enough currents, and then it approaches the flux flow region. Now, when we turn on the temperature, there are now it works. There are two effects. The first one is creep, which is a small vortex velocity even for subcritical drives. And the other one is the thermal deepening, which is essentially the thermal renormalization of the critical current. So the advantage of strong pinning theory is that it allows us to do the analysis non-perturbatively, because in strong pinning, the current velocity characteristic can be calculated from this dissipative balance equation, and the only quantity that we need to understand is this pinning force density. So this is the central object of our attention, and I will describe how to calculate this. We have already seen, so I will briefly go through this formalism of strong pinning. It turns out that the very complicated system of vortices, where displacement at every part is important and vortices interacting with each other, can be simplified to provide us with a simple model which just contains a vortex elasticity through an effective constant C bar. And then, like in some sense, what I will talk about is not much different from a statistical physics of a harmonic oscillator, because the vortex behaves like an harmonic oscillator. Now, if we place this harmonic oscillator into a trapping potential, into the potential due to the defect, this EP of R, if the defect is sufficiently strong, the vortex can exhibit two states. One state is free, when it essentially doesn't feel the defect. The other one pinned, when it's trapped to the defect, and if you try to shake the vortex, you see that the tip of the vortex doesn't do much. Now, why we call this strong pinning? It's strong because when we plot this total pinning energy and try to find the position of the defect, we find that there are those two solutions characteristic for strong pinning, only in the case that the potential due to the defect is sufficiently strong. You can imagine that if we made this potential shallower, then the second well here would disappear. And then one can do the mathematics and formulate this in terms of a precise condition. So in the next two slides, I will essentially give a very intuitive idea of how creep works in strong pinning. First of all, if there is no creep, the pinning force in strong pinning results from the asymmetry. The asymmetry is due to the fact that vortices get trapped very easily, but it's hard for them to deepin, which means that the force produced during the deepening process is larger than the force that attracts the vortices to the defect. And then when one calculates the average force, unlike in the weak pinning regime, one gets a non-zero answer. How this is changed for finite temperature? Well, if the temperature is finite, it's easier for the vortex to overcome the barriers associated with pinning and deepening. And in the end, the vortex gets trapped a bit earlier and it depends a bit earlier. This means that the force attracting the vortex to the defect is larger than in the previous case, and the force opposing the motion during the depinning is smaller, and in the end, we get a pinning force reduction. So now I need to go into a bit more formalism to explain how one can calculate this force quantitatively. I need to introduce this somewhat complicated object that we call multi-valued energy landscape. So the way to introduce it is to look at the pinning energy that we had before. Now we want to, given the asymptotic vortex position, we want to solve for the position of the vortex tip. And in the strong pinning regime, as we have seen, this gives us multiple solutions. Now when we plug those multiple solutions back to the pinning energy, we may obtain a multi-valued energy landscape. And this is exactly the quantity that is plotted here. It is this energy which depends only on x. Since the vortex can be pinned or unpinned, the energy has two branches. The parabolic one corresponds to the energy of pinned vortices, and those nearly flat branches correspond to the energy of free vortices. Then there is also an unstable branch, which is very important in the context of creep. It connects those two branches, and it originates from maximizing the energy here and plugging back the solution which maximizes the energy. So the thing that we have to do is to find out how those branches are occupied, which vortex state is realized. For this, we were inspired by the work of Brazowski and Larkin, who studied a similar energy landscape in the context of pinned charge density waves, which develop a similar instability. And the problem can be formulated in terms of the rate equation, which in the steady state looks like that, and it tells us what is the fraction of pinned vortices. Of course, if you look at the energy landscape, in some of the pairs we don't have to work at all, because, for instance, here only the free branch is available, so the fraction of pinned vortices is 0. Then here in the middle, the vortices can be pinned only and nothing else. And here again, the fraction of pinned vortices is 0. But in between, we have to solve this equation, and we can regard this like if the vortices are dragged in one direction, we can regard this as an initial value problem, starting the solving for those multi-valued intervals, starting either at this or that point. So now, let's forget for a moment about temperature. And if temperature is 0, the transitions across the energy barriers are not possible. And therefore, the occupation of the branches doesn't change. It stays constant as long as it's possible, which means that if the vortices are dragged in this direction, they are of course free in the beginning, and then they continue moving on the free branch, even though at this moment the energy of the pinned vortices would be more favorable. They have no mean to overcome this energy barrier, and so they get pinned only at this end point when the free branch is no longer available. And then the scenario repeats, and what you see here is exactly the asymmetry that was shown on the picture before. Then one can calculate the pinning force, and when one expresses it as the average derivative of this energy, it turns out that the answer is very simple, and the average pinning force just depends on the sum of those two energy jumps. So this is the occupation that we had before. Now, when we turn on the temperature, we found that one has to look separately at two regimes. One regime is large drives for currents comparable to the critical current when the vortex velocity is large. And now, when vortices are moving on this multi-valued energy landscape, at this moment, they see that the energy of the pinned branch is more favorable. They may overcome the energy barrier, but since the drives are high, they end up nearly close to this endpoint, which means that they just jump a little bit earlier than in the previous situation, which leads to the renormalized energy steps. when we look at the rate equation and solve it, we find that those energy steps have a very well-defined position, which is given by the barrier. If we know the velocity of the vortex lattice and temperature, we simply search for the barrier in this energy landscape, for the distance between the pinned and unstable branch. And when this barrier attains this particular value, this is the point where the jump is realized. So then translating to this formula, we are able to say what is the pinning force as a function of temperature and velocity. This is quite different at small drives, because when drives are small, the system is nearly close to equilibrium, and those jumps that we had before disappear. Here our analysis actually differs from the one by Larkin and Ovchinnikov, and we believe that we have provided a better understanding of this situation. The thing is that now, if the system is fully at equilibrium, always the branch with the lower energy is occupied. And in order to find the pinning force, one needs to look precisely of what is the development of this occupation around those points of equal energy. So the red curve here is the development of the equilibrium occupation, which changes smoothly from 1 to 0. And then the yellow curve shows the development of our steady state vortex occupation of branches. What we found is that this occupation is slightly shifted from the equilibrium one, and the important fact is that this shift is linear in velocity. So then, when one calculates the pinning force, in this case it can be essentially understood as an area between the equilibrium and steady state occupation, because if vortices are in thermal equilibrium, there is no average force exerted on them. And then the resulting pinning force is also linear on velocity and depends on this activation barrier U0. And we know precisely what the activation barrier is, because once we know how the energy landscape looks like, we can simply read it by looking at this point where branches have equal energy. Okay, so now we have enough information to calculate the current velocity characteristic. We simply plug in the formulas calculated by one of those methods described before. And as a result, at small velocities, everything is linear. So the velocity of the vortex lattice depends linearly on current, and it enters this thermally assisted flux flow regime when the activation barrier, as I said before, can be read from the energy landscape. Then at higher drives, there are some nonlinear effects playing a role, and at some driving current, which we call JDP, we see a sudden increase of the slope, and the vortex is thermally depinned. So we have calculated a formula which describes the temperature reduction of the critical current to the depinning current, and a good quantity to understand those current velocity characteristics is the deepening temperature, which basically, in this sense, we define the deepening temperature in a way that if the temperature of the system is comparable with the deepening temperature, like on this picture, then the vortices no longer feel the defects and the system is fully deepened, doesn't know about pinning. So now, let me show you some numerical results. The blue curve is the current velocity characteristic at 0 temperature, and now we increase the temperature and we see that this reduces the critical current, and like from when the temperature is half of the deepening temperature, which means that the temperature is about 5% of the depth of the pinning energy, of the depth of the pinning potential well, then the vortices are already fully depinned and they don't feel the pinning landscape. Let me draw a correspondence of this with a paper by Ambegawkar and Halperin, who studied the transport through the Josephson junctions, and it's well known that the transport through the Josephson junction is governed by the same equation as motion of particle in this periodic potential. And when external current is applied, the periodic potential is essentially tilted, and the voltage through the Josephson junction can be described as a thermally activated motion of the particles through the washboard potential. I mean, one needs to tilt the head here because they plot the current on y-axis and voltage on x-axis. But what we see here is essentially the same form of thermal deepening, because when one looks closer, like it, I'm not sure if it's visible, but one may see that there are some points of the sudden rise of curvature in the characteristic, and it is the same that we observe here. But at the same time, one has to be careful in comparison of our current voltage characteristic with this simple model of tilted periodic potential, because when we look at the barrier as a function of current, which is important to describe the decay of persistent currents, then at low temperatures, we actually recover the result that would be valid for this tilted periodic potential, which is that the barrier vanishes close to the critical current with this power of 3/2, which we have seen before, and it is somehow characteristic for the one-dimensional systems. But later, when we increase the temperature, we actually see that, we see that the barrier increases with temperature. And close to the critical drives, we no longer see this vanishing of the barrier. And we have calculated this value and found that later the barrier varies only logarithmically. And now I want to stress that this correspondence with the tilted periodic potential is not really appropriate. One should think in terms of this multi-valued energy landscape. And the fact that we have this familiar 3/2 scaling comes from the, sorry, now I messed up with the order. Okay, the fact that we have this 3/2 coefficient in the scaling comes from the fact that when one looks at the development of the barrier close to the endpoint of the multi-valued interval, then it also scales with this power of 3/2. But, so this is the picture which is valid at low temperatures close to the critical current. But when the temperature is increased, the picture looks like that. The jumps are realized a bit earlier. And it means that even though the system is driven by currents close to the critical ones, we jump at a finite barrier. We jump at the points which correspond to a finite barrier. This is, of course, also very different from what we know from the weak collective pinning. Now, let's concentrate back on the case of small drives. In the weak collective pinning theory, when actually the description, well, we can imagine that vortices create some complicated mountain-like landscape, and applying external current means basically tilting this landscape. When this tilting is small, we have to displace a huge part of the vortex in order to jump into an energetically more favorable valley, and this is associated with huge free energy fluctuations, and the activation barrier for small drives vanishes. One shouldn't think about in terms of tilting in the regime of strong pinning. Instead, if the applied current is small, we still have this situation where vortices can be either pinned or free, and they are separated by a critical nucleus, and this critical nucleus has a well-defined energy that we can calculate. And it means that in this regime of strong pinning, we enter the thermally assisted flux flow regime with a linear dependence on a driving current. But at the same time, we are aware that perhaps at very low velocities or very low drives, we would have some collective effects which would in fact recover the situation that is familiar from the weak pinning. So now I just display the part of the current velocity characteristic which exhibits this linear tuff. And when one considers spinning due to clusters of defects, then since the cluster of two defects has a twice higher activation energy than isolated defects, the slope of this curve is smaller than just for isolated defects. And if one considers clusters of three defects, it's even steeper in this j direction. And I mean, now the correct way to read this picture is again tilt our head and ask the question, given the vortex velocity, what is the driving force or the driving current? So then one needs to sum all those curves in this horizontal direction, and we can obtain the resulting characteristic at extremely small velocities as an envelope of those curves. And then this envelope departs non-linearly from the origin, and we can in fact get back to the we can somehow draw a correspondence with the weak pinning regime with this logarithmic-like divergence of the activation barrier. Okay, so let me just flash a summary of what we did. So we considered strong pinning theory, and we have calculated the effect of thermal creep. We have calculated the current velocity characteristic, which exhibit the linear tuff regime at low drives and the renormalization of the critical current. Okay, thank you.